Good morning one and all. Welcome to the lecture on electrical circuit analysis. So, today topic is on maximum power transfer theorem. So, today lecture, so let us see the maximum power transfer theorem. So, the lecture objective is to state the maximum power transfer theorem. So, what is the statement of this maximum power transfer theorem, and the next objective is to apply the maximum power transfer theorem for solving the given network. That means, how we are going to solve the given problem by using this maximum power transfer theorem. So, what is the application of this maximum power transfer theorem? Okay. So, this maximum power transfer theorem states that, okay, what is the statement of this maximum power transfer theorem? The maximum power transfer theorem states that the maximum power is transferred from source to load when the load resistance is equal to the Thevenin's resistance as seen by the load. What is the statement of the maximum power transfer theorem? The maximum power is transferred from source to load when this load resistance must be equal to the, that RL load resistance must be equal to the Thevenin's resistance seen from the terminals, that is the equivalent resistance seen from the terminals. So, this is the statement of the maximum power transfer theorem. Okay. So, how much amount of maximum power is transferred? How much amount of maximum power is transferred from source to the load? Okay. So, according to this maximum power transfer theorem, okay, so what is the power drawn by this load means P is equal to I square into RL. That means, we know that power is equal to I square into R. So, I square into RL. So, this RL, so what is I? So, I is when you obtain the Thevenin equivalent circuit for the given network. So, then you can easily find out the current flowing in the network, that is V Thevenins by R Thevenins, and plus this series resistance, that is load resistance, is connected in series. Therefore, I P is equal to V Thevenins by R Thevenins plus RL whole square into RL. So, this much amount of power is maximum power is transferred from source to the load. Now, if you see this waveform, okay, this graph, so 0, so 0 to RL, the load resistance is varying from 0 to RL, then the power is from 0 to P, it is varying. So, as the load resistance is changing, okay, as the load resistance is changing, load is changing, means RL is changing, the power drawn by the load is increasing. So, at a point, this source will deliver the maximum power to the load when this RL must be equal to the R Thevenins. Now, see this figure. So, RL must be equal to the R Thevenins. Whenever this RL is equal to R Thevenins, then the maximum power is transferred from source to the load. Okay. So, let us derive this condition. So, when I told you the statement, the maximum power is transferred from source to load when load resistance RL is equal to the source resistance. It is not RS is equal to RS, it is not source resistance is equal to load resistance, it is load resistance is equal to the source resistance. It means load is always varying, load is not constant, but source resistance is constant. Therefore, RL must be equal to, when the maximum power is transferred means RL is equal to RS. So, if RL is equal to RS, do not say that RS is equal to RS, RS is equal to RL. So, in the mathematical equation, if A is equal to B means B is equal to A, it is possible for only mathematics, but it is a practical situation here. So, the maximum power is transferred from source to load when load resistance must be equal to the source resistance. Okay, when load resistance is equal to the source resistance. So, we will get the question, maximum power is transferred when option A RL is equal to RS, option B RS is equal to RL, option C both, option D none. And which one is correct answer? Option A, load resistance is equal to the source resistance, RL is equal to RS. Okay. See, if you want to confuse you, he also given the option B, RS is equal to RL. If you pick the B, so you will be right, that will be wrong answer. And also again the both, C is both A and B, so it is also wrong answer. Therefore, you have to select the proper answer. The maximum power is transferred from source to load when load resistance is equal to the source resistance. Yes or no? So, whenever when I am delivering the lecture, whenever maximum content is transferred from lecturer to the student, that means your intensity, your understanding level must come to my understanding level. Okay. So, how you have to think, that is the way to understand this maximum power transfer theorem. Okay. Now, so let us derive the condition. Now, see, so to get already for mathematics, to get the maximum minimum condition, you have to differentiate that equation with respect to the variable. Here, what is the variable here? So, because here load is changing, see load RL is changing. So, I am differentiating this equation P, power equation with respect to the RL. So, dP by dRL is equal to the R. Now, we are see P Thevenin's by R Thevenin's plus RL whole square into RL. So, you use the UV method, that is a UV method differentiation. So, U into V dash plus V into U dash. Okay. Now, see here. So, first V Thevenin square into V Thevenin square. V Thevenin is a constant, it is a value. So, keep it out outside V Thevenin square. So, 1 by R Thevenin plus RL whole square into RL. Okay. So, R Thevenin's U by V method, U into V dash, sorry UV not into U by V, it is not UV method, it is U by V method, U into V dash plus V into U dash. Okay. So, therefore, so R Thevenin plus RL whole square, that is a V U into V dash. So, what is a V? So, V is a VRL. So, RL D by DRL of RL is 1. So, R Thevenin plus RL whole square minus now U into V dash is over. Now, V into U dash, what is V? R Thevenin plus RL. Okay, RL is V. So, RL into R Thevenin plus RL whole square is 2 into R Thevenin plus RL into R Thevenin is 0, RL is 1. So, therefore, by P square, so R Thevenin plus RL square whole square, that is R Thevenin plus RL whole to the power of 4. Okay. So, therefore, now in order to get the maximum and minimum condition, you have to differentiate the equation and equate to 0. So, now you equate this total entire equation to 0. So, 0 equal to R Thevenin plus RL. So, minus here you please expand this R Thevenin plus RL whole square, A plus B whole square formula, A square plus B square plus 2AB. So, therefore, R Thevenin square plus RL square plus 2 into R Thevenin into RL minus 2 into R Thevenin into RL. So, cancel, both will cancel and here RL is there. So, therefore, you will get R Thevenin plus RL minus 2 into RL, 2 into RL. So, RL minus 2 RL is RL. So, therefore, 0 is equal to R Thevenin minus RL, that is equal to RL is equal to R Thevenin. So, do not write that R Thevenin is equal to RL here. So, the load resistance must be equal to the source resistance. Source resistance means the resistance seen from these load terminals, that is Thevenin's resistance. RL is equal to R Thevenin. So, now if you substitute this RL is equal to R Thevenin in this equation, power equation. So, V Thevenin by R Thevenin plus RL is equal to R Thevenin. R Thevenin plus R Thevenin, 2 R Thevenin. So, 2 R Thevenin, that is V Thevenin square by 2 square is 4 R Thevenin into R Thevenin. R Thevenin will cancel. Therefore, V Thevenin square by 4 into R Thevenin. This is the power equation. So, this much amount of power, the maximum power is transferred from source to load when this RL load resistance is must be equal to the source, or that is Thevenin's resistance. Load resistance is equal to the Thevenin's resistance. So, this is the statement of the maximum power transfer theorem. Okay. So, this is the statement of the maximum power transfer theorem. Okay, that means whenever this value, this load resistance value is equal to the Thevenin's resistance, this RSC, R Thevenin's, RTH, then the maximum power is transferred from source to the load, source to the load. That is the condition here. Okay. So, let us solve one problem on this maximum power transfer theorem. Now, find the value of RL, that is a load resistance, for maximum power transfer theorem, that is for maximum power is transferred from source to load. In order to transfer the maximum power from 12 volt source to 2 ampere, that is a RL load resistance. So, what must be the value of this RL? What must be the value of this RL? So, if you are good in the how to solve this Thevenin equivalent circuits, Thevenin resistance and Thevenin's voltage, then it is easy to solve easy to apply the maximum power transfer theorem. Now, see here. For here, I have to apply first find out the R Thevenins. Okay, R Thevenins. So, see, to find out this R Thevenins, so making the independent sources are 0. That means voltage source is short circuited, current source is open circuited. If you redraw the network, this is the network. So, 6 ohms, 12 ohms, 3 ohms and 2 ohms. See here, voltage source 12 volt to voltage source is short circuited, 2 ampere current source is open circuit. So, this is the circuit. Now we have to find out, remove this RL. See, when you are finding Thevenin's equivalent circuit or Thevenin resistance or voltage. So, you have to remove the disconnect the load resistance, disconnect the element at which terminals you want to calculate the Thevenin equivalent resistance and voltage, Thevenin's voltage. So, I have disconnected that. So, therefore, I want to find out the R Thevenins from the terminals A B. So, these terminals A and B. So, same terminals A and B. Now, tell me, when you are coming from the right side, so when you calculate the equivalent resistance, you have to go from the left side. So, 6 ohms and 12 ohms both are in parallel. Okay, 6 ohms and 12 ohms both are in parallel. So, whatever this combination will get in series with a 3 ohm resistor plus 2 ohm resistor. Therefore, what is 6 into 12? See, 2 plus 3 is 5 plus 6 into 6 is parallel with 12. So, 6 into 12 by 6 plus 12, 18. Okay, 18 by, so you will get the 9 ohms. 9 ohms. This is the R Thevenins. That means R Thevenins is 9 ohms means, what you are understanding? So, R Thevenins is 9 ohms means, see, the maximum power is transferred from source to this RL when this RL value is equal to the 9 ohms. That is what the meaning. Now, how much amount of power is transferred? Let us calculate. Okay. To calculate that, I am going to find the R Thevenins. Okay. So, first find out the V Thevenins, R Thevenins over V Thevenins across the terminals AB. Now, I am using here 2 meshes here, mesh 1 and mesh 2. So, current is assuming that that is mesh analysis, clockwise direction I1 and I2. Now, apply the Kirchhoff voltage law in each and every mesh individually. So, first apply the Kirchhoff voltage law in the first loop. Okay. So, what is what? So, first one is minus 12 volts plus 6 plus 6 ohms and 12 ohms are in first mesh. Therefore, 6 plus 12 is 18 I1 minus this 12 ohm resistor is connected, that is between the 2 meshes. Therefore, minus 12 I2 okay, is equal to 0. Sorry, I forgot to write, is equal to 0. So, algebraic sum of the voltages around any closed path is equal to 0. But what is I2? So, I2 already given that here, see, I 2 amperes current, 2 ampere is flowing outside means 2 ampere going from bottom to top means, so I2 is equal to minus 2 amperes. Now, apply the mesh analysis, that is Kirchhoff current law from this 12 volts voltage source to 6 ohm resistor, 3 ohm resistor and 2 ohm resistor and V Thevenins and come to the back minus 12. Therefore, minus 12 plus 6 into, now see here 6 into I1 plus 3 into I2 plus 2 into I2, that is 0 because open circuit na, P Thevenins open circuit, so 2 into 0 plus V Thevenins is equal to the 0. But see, you got the first equation here. So, substitute this I2 is equal to minus 2 amperes in this equation. So, minus 12 plus 18 to 18 I1 minus 12, 18 into I1 is minus 2. So, 18 to the, sorry, 18 I1 minus 12 into I2. What is I2? So, I2 is 2, minus 2. So, 12 to the 24. So, 24, yes or no? 24, minus into minus plus 24. 24 minus 12, how much? 12. That means you will get here 1 ampere. Now, substitute the 1 ampere in this equation, I1 is equal to 1 ampere. Okay, minus 12 plus 6 into 1 plus 3 into I2 plus 2 into 0. So, these are 6 into I1 is, there is no I1 here because I1 value is 1 here. So, 6 into I1 plus 3 I2 plus 2 into 0 plus V Thevenins is equal to 0. So, if you solve this equation, then you will get the V Thevenins value is 22 volts. 22 volts. Then what is the maximum power? Already we got that RL is equal to R Thevenins, that is the 9 ohms. So, P maximum power is transferred, the value is V Thevenin square by 4 into R Thevenins. So, that is equal to P Thevenins is 22 volts by, that is 22 square by 4 into RL is 9 ohms, that is 13.44 watts. That means what you understood from this problem means, so this is the example problem. So, the maximum power is transferred from source to the load when this RL value is equal to the Thevenin's resistance, that is 9 ohms, and how much amount of that maximum power means, so how much? 13.44 watts. And also, whenever this maximum power is transferred from source to the load, okay, so what is the, how much amount of voltage will get appear across this equivalent resistance, that is the Thevenin's resistance. Okay, how much amount of will voltage? See, 50% of the voltage will get, because see these two values are equal, R Thevenins and RL are equal. So, if you apply the voltage division principle in this series current elements, So, if it is 100 volts source voltage, so 50 volts will get appear across this R Thevenin's and 50 volts will get across the load resistance. That means, during the maximum power transfer, so 50% of the voltage will get appear across the Thevenin's resistance seen across the low terminals and the load resistance. So, this is the maximum power transfer theorem statement, and we'll solve one example problem to understand the maximum power transfer theorem. Okay? Thank you. So, we will join in the next class.